This video is entitled Directional Derivatives. And a directional derivative at a point in the direction of vector u is the value of a slope at that point towards vector u. Because the concept of tangent slope in 3 dimensions doesn't really work the same way, as in 2 dimensions, because you can have a dot spot like up here on this graph, and you can draw infinite number of tangent lines in 3 dimensions to that spot. But we're interested if we have a direction vector that tells us, okay, then we want to know the tangent slope as the line goes parallel to the direction vector given in the problem. We can find that. And in fact, we've actually already have learned a couple directional derivatives. If you take the x partial of a function, you take the x partial at a point, you are actually finding out the tangent slope as it goes along the x-axis direction. And then the y partial would be the same thing, that goes along the direction of the y-axis. But any other random direction, like it has this picture right here, has to be specified by a vector to indicate, where we want our tangent line to be heading towards, because that's the only way we can get a slope. Because like I said before, otherwise it's infinite with no answer. Now, there's a couple ways you can do this. Now, if we don't have a vector, we can also have an angle theta coming away from the x-axis. So that's the first way we'll learn to do it. Then we'll learn to do it another way. So if you have theta, then this unit vector u will be cosine of theta I sine of theta j. So the directional derivative will be the partial of x, plug in the point, times cosine of theta, plus the partial of y, plug in the point, sine theta. So you see that it has d, and the subscript u means in the direction of u of your function f of xy. So that's really not too bad. Of course, obviously assuming that your directional derivative is not some, monstrosity or something, but I certainly tend to avoid that for my students. Find the directional derivative at the point 1, 2 in the direction of theta equals pi over 3. Of the function f of xy equals x squared minus 2xy squared plus 3y to the 4th. So let's take the partials. So respect to x, it'd be 2x. Get rid of the x here, it'd be minus 2y squared, nothing there. And then respect to y, there's no y term here. Derivative of y squared is 2y, so it's negative 4xy. And then 12 plus 12y cubed. And then put in 1, 2 into this first one, so f of x at 1, 2 will be negative 6. And f of y, 1, 2 will be 88. And then you would take, so you got negative 6 times cosine of pi over 3 plus 88 times sine pi over 3. The exact answer is negative 3 plus 44 square root of 3. Now I never can sometimes figure out what's the best way to line these graphs up here. I don't think I did a very good job of it here, but I was just trying to indicate the pi over 3 direction and then the points up here. So I'm trying to draw the slope going in that direction. Oh, well, that's all right. Well, obviously it's a very steep positive number, so it's going to be heading upward as you head toward that pi over 3 angle. It's going to be increasing very steeply. So maybe I should consider regraphing this one day and making it look a little better if possible. Well, that's all right. But that's not important because you don't have to do that. You just have to do the calculation. This next one will be a little bit better to visualize, I think. Find the directional derivative at square root of 3 in the direction of theta equals pi over 6 for z equals 9 minus x squared minus y squared. So easy partials, so it'll be negative 2x for the zx, and then zy will be negative 2y. So if you put in the point pi over 3, you're going to get negative 2 square root of 3 for both of those. So the directional derivative at that point, square root of 3, will be negative 2 root 3 times cosine of pi over 6, square root of 3 over 2. Negative 2 root 3 sine pi over 6, that's 1/2. And you end up with the exact answer of negative 3 minus square root of 3. That's roughly about negative 4.7. So here's what I'm kind of drawing where pi over 6 is. And this red dot represents the point square root of 3, square root of 3. And then the green line is kind of the tangent line. So heading in the direction of this, well, they look like, obviously this is on the xy plane, but this line would be going downward. So it's a negative slope. So that one's a little better visual than the last one, but anyway, the calculation's not too bad. That's the important thing. Now let's talk about something called the gradient of a function of two vectors. And we'll see what geometrically what the gradient tells us. We'll learn that a little bit later, but now we'll just see how to calculate it. When you are finding the gradient of a function, it is a vector. So here's your function z equals f of xy. Then the gradient, this is often known as del. We'll say del f or whatever. Yeah, del f right there. Keep in mind that the idea is that this is called a mathematical operator, meaning by itself it doesn't mean anything. So you could never say, let me try to do this. It's not going to look very good. But if you said like del equals, like this, that's not correct form, because when we say mathematical operator, that means it has to have something to act on to mean anything. In other words, by itself, it has no meaning. So as soon as you put this, apply it to the function of f of xy, you are creating a vector. That is, of course, we can use component form here. They're using standard unit vector form, but we can use component form. And it's the fx would be the I component, and fy would be the j component. Now, if it's three variables, it would look like this. So I just wrote it in component form here. It's a vector, either a two vector space vector, plane vector, or a space vector. Now, this is telling you here that for each xy, the gradient is a vector in the plane, not a vector in space, but in a three-dimensional idea, it'll be a vector in space. So it's just the fx partial, the fy partial to find the gradient, because this is about to lead us to another way to do find the directional derivative. So now we're just finding the gradient for this function, f of xy, e to the 3x, tan of 4y. This will test our derivative skills a little bit here. The x partial of this, the derivative of e to the 3x, because the chain rule of the 3x will be 3e to the 3x times tan of 4y. Then the derivative of tan of 4y is sec squared 4y, but it's 4 sec squared 4y, because once again the chain rule here, you have to take the derivative of the 4y. So I just put the 4 out in front here to make it look better. So it'd be 4e to the 3x sec squared 4y. Alright, so there you go. There's the gradient. Of course, obviously, like the next one here, they're asking it at a point. That one did not. That was just the general variable form of the gradient. So z equals natural log of x squared minus y. So the derivative of natural log basically is u prime, the derivative of the inside over the inside. So both of these have x squared minus y as the denominator. But the derivative of the inside with respect to x would be 2x. And then for the other one, the derivative of the inside with respect to y would be negative 1. So those would be your two numerators. And now we put in 0.23. So 2,3 gives you 2 squared minus 3. So the denominator is 1 for both of these. So it's 2 times x, which is 2 times 2, makes that 4. And then negative 1 is just constant, so it's 4 comma negative 1. Now here's the gradient for a function of x, y, and z at the point 2, negative 1, 3. So let's take each partial, the x partial, so right here would be the x would go away, so it leaves 2z squared. The middle term has no x, so it would be 0. The last one is 4x squared, so it's just going to be 8x. So it would be 2z squared plus 8x. The next one, with respect to y, the first term and the third term do not have a y, only the middle. So the derivative of negative 3y squared is basically negative 6y with the z cubed attached. So it's negative 6y z cubed. And then the z partial, the last term doesn't have a z, but the first two do have one. So it would be z squared would be 2z, so it makes it 4xz, and then z cubed would be 3z squared, so 3 times that 3 with a negative there makes that negative 9, y squared z squared. So there's the gradient written in component form as a vector, and then it's asking this at 2, negative 1, and 3, so I'm not going to go through the steps here, but just plug in at 2 for x, negative 1 for y, and 3 for z, and you should come up with a vector of 34, 62, negative 57. Dot product form of the directional derivative. So now this is going to be, in other words, we're going to be given a direction vector instead of an angle. We saw before if it gave you an angle theta, and then your direction vector was automatically cos theta sine theta. So now we're going to have some sort of random, direction vector. It could be like, 2i plus 5j or something. So here's how we handle a directional derivative in directional derivative in vector form. Now, unit vector, this is going to be very, very important. You'll watch when I do these. In fact, Stewie's telling you here that your direction vector, if it's not already a unit vector, which it won't be most of the time, you must convert it to a unit vector. See, when we did cosine and sine earlier, that was a unit vector because it basically, was based off the values were based off the unit circle. But here, not so much. If you do not convert it to a unit vector, you'll get the wrong computational answer. So the directional derivative, so if you do that, it's actually easy. You just take the gradient at the point x, y, z, and you dot it with that unit vector that indicates the direction it's going. And that's going to tell you the directional derivative, which is the slope that will be in the direction of that vector u. So now we have one, here's our function in terms of x and y. 3x squared minus y squared plus 4. And then we have pq. Find the directional derivative at p, so that's your point value in the direction of q. All right, this goes way back to the beginning of the course when we were learning about vectors. Is that when you have 2 points, so if it's going from P to Q, we want to calculate the vector PQ. So it goes way back to the very beginning. So, but it's easy. 3 minus a minus 1 makes 4. 6 minus 4 makes 2. So your PQ vector would be 4 comma 2. And using a property of magnitudes, I did factor out a common 2 there. I didn't have to, but I did. Makes it a little easier. These numbers are small, it doesn't matter. That helps when the numbers are larger for sure. So I pulled the 2, and that's why, so you have 2 squared, and then half of 2 is 1, plus 1 squared, so it's 2 square root of 5. That's your magnitude. That's important because, obviously, you right there, see the magnitude, it's not 1, is it? So the magnitude's not 1, therefore it's not a unit vector, and it needs to be converted to a unit vector. So we had to have that magnitude. I forgot to mention that. Obviously, I just looked at that, and I knew the vector wasn't going to be, a length of 1. So, but its length is 2 square root of 5. So we have to divide vector PQ by 2 square root of 5. So that's what I'm doing right here to convert this to a unit vector. So it's PQ divided by its magnitude. So I took 1 over 2 square root of 5, multiplied it by 4, 2, and came up with this result. And I don't mind, some instructors may bother them, but it doesn't bother me if if you don't rationalize the denominator. But you could easily check. I mean, I'm not going to do it because I can see it is, but that does have a magnitude of 1 if you check the magnitude of it now. So, and it's going the same direction. So we have our unit vector. Now we need our gradient. So this is a pretty easy one. So the fx partial is easy right here. Just be 6x. Fy partial, derivative right there, be negative 2y. And we're saying at p, so use the point p. So put in negative 1, put in 4, negative 1 for x, 4 for y. You get negative 6, negative 8. So all we have to do is take that gradient at negative 1 and 4 and dot it with that unit vector right there above it. You remember, these directional derivatives are always scalar answers. They're numerical answers, not vector answers. Obviously, anytime you do a dot product, you always have a scalar. So negative 6, negative 8, dot 2 root 5, 1 root 5. I did the little arithmetic down here, and I got negative 20 over square root of 5, which in my world is perfectly fine, but I went ahead and just for the heck of it, because let's say you were checking an answer on a quiz or a test or an answer in a book, they would probably, handwritten, that would be fine with me. But if you had to match an answer, you would have to do this step right here, and then it simplifies to negative 4 square root of 5. Or you could check on a calculator your answer choices from a decimal standpoint and see which one would be equivalent to that. That's how you would know. I showed how to do this in Maple. Probably another reason I simplified this is so it would match that Maple answer. Obviously, that's not required for you in my class, but some of you looking at this might be using Maple at some point, so you might find that handy. So it's negative 4 square root of 5. And I found some sort of plot feature of it there. Yeah, I kind of didn't know which way was the best way to show that. I think the green is the unit vector. And let's see. The blue is probably, not sure what it is. Obviously, the curve is the graph of the original function. Yeah, I'm not totally sure what that accomplished. That's all right. Oh, this got cut off, so I'm going to go. For 3 variables, essentially the same thing. Same exact formula. So the directional derivative will be the gradient of f of x, y, z dotted with that unit vector. But here's a new thing we're going to learn. Now, like I told you earlier, you take a point on a 3-dimensional surface and you technically have infinite possible slopes that you can choose on that graph. Suppose that we want to know what is the maximum slope you could get if you did all possible slopes. Fortunately, you're not going to have to test them out, so it's real easy. And then what would be the minimum, the least slope you could get? So the maximum value of all possible slopes at a point turns out being the magnitude of the gradient. That's the maximum slope of all possible slopes at a point on the graph. The minimum is the negative of the gradient. So that means any directional derivative that you calculate, which you don't have to test this every time. Obviously, you don't have to worry about the max and the min if you're being asked, but I'm going to show you how that relates here in a minute. But that means if you're doing the directional derivative at any point that's not evaluated at the gradient, it's going to be the answer has to be somewhere between that min and that max. So let's see. So I'm kind of showing that right here. So this was an example that we had back up here. This one right here, with a negative 1 and 4, and we got the directional derivative was negative 4 square root of 5. Well, anyway, the maximum value, the gradient at negative 1, 4, see, was negative 6, 8. That we had that right up in here, right? Should be right there. So that we're using that gradient right there, and then we're taking the magnitude of it and the negative magnitude of it. So the magnitude is 10, and then the negative magnitude is negative 10. So that means the directional derivative that we figured out at that point, and of course it was heading to whatever that other point is, I'll have to go check and see whatever vector that generated, had to be somewhere between negative 10 and 10. And that was the one where we got negative 4 square root of 5, I believe, right? Yeah. Yeah, negative 4 square root of 5 is somewhere, that's about negative 9. It's kind of close to, somewhere toward negative 9 point something. It's toward the negative 10 area, but it's still staying, between the min and the max. So here's one with 3 variables. We want to find the directional derivative at P, and this time it gives us a vector u instead of 2 points. Vector v, excuse me. Vector v. That is 2, 1, negative 1. That's definitely not going to be a unit vector. In fact, you come down here and you see its magnitude is actually the square root of 6. So obviously not a unit vector. So the magnitude is square root of 6. And we have to convert then this vector into a unit vector by dividing each term by the square root of 6. So we have 2 over square root of 6, 1 over square root of 6, negative 1 over square root of 6. And let's go back up here and look at the gradient with each partials. So the x's only appear the first and the third term. So it'd be y plus z for the first one. The y are the first 2 terms, so the partial would be x plus z. And then the z's appear the last 2 terms, y plus x. So if I put in 1, 2, negative 1 into this vector right here, easy calculation, so I don't think I have to go through that, you'll get 1, 0, 3. That will be our gradient vector at that point. So we take that gradient vector, we dot it with that unit vector right below it, and that will be our directional derivative. And I got negative 1 over square root of 6. Okay, so now I'm asking for the maximum and minimum value of the directional derivative at that point. What's the largest one it could go? It could be. And so obviously my answer I have here will have to be a number that's between whatever that min and max is, because it's a vector that's not going to be where the maximum is going to be the gradient anyway. So so I do the 1, 0, 3, the magnitude is square root of 10. That's the maximum possible directional derivative, and the minimum would be negative square root of 10. And my value, negative 1 divided by square root of 6, is clearly between these 2 numbers. So that's good news. And that's what I just kind of wrote out right here. Yeah, it's occurring at the gradient. It's going to be where the maximum and the min are occurring in the direction of the gradient. I think we'll be defining that a little more formally. If I don't define it formally, let me see if that's going to be coming up. If not, then I'm going to say it. Yeah, it's kind of coming up here. All right, here's one. Interesting f of x, y, z. We got e, we got cosine, we got sine. Here's your point. 0, pi over 2, pi over 2. Vector 2, negative 1, 2. That will not be a unit vector, obviously. So we're going to find the directional derivative in the direction of u of f of 0, pi over 2, pi over 2. So let's get the gradient vector. Actually, this looks complicated, but actually it's easy because you don't have multiple variables there, so each x, y, and z are separate. So the derivative of e to the 2x will be 2e to the 2x, with those other 2 being attached because it's multiplied. The middle one, the derivative of cosine of y, will be negative sine of y. So it puts a negative out here. So negative e to the 2x sine of y sine of z. And the last one, the derivative of sine of z is positive cosine of z. So that leaves everything positive here and makes that cosine. And then you put in 0, pi over 2, pi over 2. Works out real conveniently here because anywhere you can find a 0, cosine of pi over 2 is 0, so it makes everything 0. The last one's another cosine of pi over 2, makes that 0. But the middle one, e to the 0 is 1, so it's negative 1. Sine of pi over 2, sine of pi over 2 are both 1. So essentially it's a negative 1 times 1 times 1, which of course will be negative 1. Now the magnitude of this original vector, magnitude, square root of 4 plus 1 plus 4, which worked out to be exactly 3. So we take our vector and divide it by 3. So we end up with 2 over 3, negative 1 over 3, 2 over 3. So we take that vector, 2 over 3, negative 1 over 3, 2 over 3, and we dot it with the gradient, 0, negative 1, and 0. Well, since 2 of those are zeros, all we have to do is multiply the middle terms. Negative 1 times negative 1/3 makes positive 1/3. And just for grins, I entered that in Maple. And let's see if Maple agrees with me there. All right, that's wonderful. Looks like I didn't try the crazy graph. This one probably would have really had a crazy graph. So we might not be able to tell too much from it, but let's come down here and look at some properties of the gradient. Oh, overshot it. All right, okay, if the gradient vector is the 0 vector, then your directional derivative will be 0. So I'll certainly avoid that, on test. But so the direction, so the maximum value of the directional derivative will be the magnitude of the gradient, but the direction it's going is in the direction of the gradient. So it's the magnitude of the gradient going in the direction of that gradient vector. And then the minimum is going the opposite direction of that gradient vector. So you see the direction of minimum increase is going in the direction of the negative gradient, and then the minimum value, the numerical value of that slope, is the negative of the magnitude of that gradient. So the gradient is the maximum, it's the direction of where that maximum derivative is occurring. Gradient is normal to level curves. We'll be using that in the section on tangent planes here coming up in another video. It's a vector that normal sticks out of there 90 degrees. Here's one plane, so each gradient vector you see at that point is going 90 degrees away from the curve, exactly, a 90-degree angle. And then it's 90 degrees in space also too. So it's orthogonal at that point. So the gradient is normal to the level curves, essentially. Okay. All right. And here's just some kind of application problem here. We're just trying to, it's not anything too complicated. Here's some function that's giving us the temperature of a point xy on a metal plate. And we're going to find the direction of greatest increase in heat from the point 3, 4. Okay, the direction just means it's the gradient. Yeah, it's the magnitude. So the direction is the gradient. The magnitude of it would be the directional derivative, the maximum directional derivative. But it wants the direction of greatest increase. So it just literally, so the direction of smallest, greatest decrease then would be the negative of this value right here. So I brought this function up instead of doing a quotient rule. You could obviously just do a quotient rule if you wanted to. But I did a product rule here for the x. I don't need a product rule for the y because I see that x is behaving as a constant. But for x, it's variables in both places. So I need to do a product rule, or I could have left it and done a quotient rule. So the derivative of x is 1. So f prime g would just leave me this part right here, minus the f, which is x, and then now I take the derivative of this. I bring down negative 1, so the product rule is normally positive there, but that now makes it negative, the negative 1 does. I reduce that to negative 2, and then I take the derivative of the inside with respect to x, and that will be 2x. And I'm not going to get too fancy, worry about trying to simplify anything, because after I figure out the y partial, all I'm doing is plugging in the 0.34 in there, so I don't really need to simplify it. Just put in 3,4 into the calculator and get it from there. We don't need to algebraically simplify it. I mean, I don't think it's going to help that much. All right, so here a little quicker and easier because it's just a chain rule, power rule, general power rule. No product or quotient rule. If you bring down the negative 1, makes that negative x. Drop that to negative 2. You take the derivative of the inside. Respect to y, it will be 2y. So I took 3 and 4, plugged it into this mess right here, even though you didn't see me do it, but I mean, just try it, plug in 3 for x, 4 for y. Kind of work it all out. I got 7 over 625. And then I've got plugging it into this one. Actually, this is a little easier. Maybe I'll explain this one real quick. But so x is 3 would be negative 3. 2 times 4 is 8. So 8 times negative 3 is a negative 24. And then 3 squared plus 4 squared is 25. And then drop down to the bottom, 25 squared is 625. That was a little easier to show. This one's a little messier here. But, obviously you can do the calculator, and it does the math frac and all that kind of stuff, so it should be easy enough. Well, that concludes this video on directional derivatives.